Okay, now add 1 to each side. Then you get 1 minus delta is less than 1. However, so that's going back to, back to principles, but this is the sort of thing that needs to be, it's like a little theorem that you use all the time, right? If you subtract a positive quantity, you make it smaller. And you got to be able to think on that level, okay? This is the explanation for why when you subtract a positive quantity, you make something smaller, right? Okay? But when you're doing inequalities, there are certain things that you've just got to keep in your mind, and you'll see this happening in the next pretty hard proof we're going to do, okay? But it's all stuff you need to be able to do. You need to be able to think about, I'm trying to make this thing smaller, or I'm trying to make this thing bigger. And you have to know what the things are you can do to make it smaller and bigger. And one way to make something smaller is to add a negative quantity to it, or subtract a positive quantity. One way you can make things larger is to add a positive quantity, okay? So that's what works there. And again, you have to be pretty quick at this, right? Or you'll take forever. So practice, practice, practice. Everybody understand this calculation here. You need to go back and do this yourself, right? You need to go back and do this. Get these inequalities straight. Everybody understand again why I needed that half in there? Yes? Okay. Let's suppose I take away, what did the half get me? Okay? The half got me that A is bigger than a half. Right? Because, again, delta is less than a half, so minus delta is bigger than minus a half. So 1 minus delta is bigger than 1 minus a half, which is a half. So did you want to know why we needed the half, or what this calculation was here? There are two questions. Okay, the reason why this calculation works is exactly the same as the reason why this one works. Because you're subtracting something that's smaller than a half. So what you get is bigger than a half. You're subtracting from 1 something smaller than a half, so you get something that's bigger than a half. That's the level you have to think about this. You can do these calculations, but you won't be able to know what to calculate if you don't think about it in that way, in terms of what's getting bigger, what's getting smaller. At least I can't do it, right? And you may have your own way of doing these things, but I can't figure out the calculation unless I first think about, okay, I need to make something bigger, I need to make something smaller. How do I go about that? Now, the reason why we had to do this is if we didn't do that, if we just took delta less than epsilon, this goes away. And if this goes away, you don't have this. And if you don't have this, you don't know that A, you could have something small. There are other things you could pick. I just picked a half because it's a nice number, right? But if you take this away, how do you show that A is in big A? Might not be, actually, right? Might not be. That's where I said you might overshoot, right? Epsilon might be so big that even when you pick it in 1 minus epsilon, it's less than 0, so it doesn't show up in there. So I've dragged the whole thing back by requiring that delta be smaller than a half. So when I go backwards, I don't go this far, I end up somewhere in here. Okay? And notice how I framed the whole thing not in terms of finding x, but I framed the whole thing in terms of how much do I subtract from 1. Right? And I wanted to subtract. So you see how that, that thinking geometric like that can help you, right? So instead of saying, well, I need to find an x in there, I thought, well, I need to find the amount that I can back off of 1 to stay inside 1 minus epsilon. Right? And so if I back off by less than epsilon, I'm good for that part. But I also want to back off by less than a half so I don't go flying out here. Now, my field is geometry and topology. I think geometrically, okay, and but I think a lot of people do that when they're doing analysis, right? Which is kind of what we're doing. And so that's how you have to think about this. You're trying to back off this. Well, you want to back off less than epsilon, so you stay in there where you're supposed to be. But just in case epsilon is huge, you want to back off less than a half. You could back off less than 1 too if you wanted to, right? And then you would still be in there. I just picked a half because it gives you a little room, right? Okay, so. But you got to do something there, or you may not wind up in A. Yes?
I think the part that I don't get is like which limit you use to define delta.
Which one of... I'm using both. You mean a half and epsilon? I'm using both. That's why I'm taking the minimum. I'm choosing a smaller than both of them. Because I have two tasks, right? One task is to get it inside 1 minus epsilon in here, and the other task is to get it inside A, which means not shooting over there. So a half accomplishes one task, and I could use 0, I could use a quarter, I could use 3/4, I could use anything in there, right? As long as right? So the half is just in there to make sure I don't overshoot, and the epsilon is in there to make sure my 1 minus delta lands in there. And it's much easier to think about A as being 1 minus delta and then adjust the size of delta so it's small enough than to think of A as being something in there and trying to figure out where it should be, right? Much easier. And the 1 minus delta fits right in with the approximation property, which uses a 1 minus epsilon, right? So you see, geometrically, you think of moving by subtracting delta rather than trying to locate A some other way. You can do it. You can do it using S2, but it's not very easy. Again, the goal here is to be lazy, right? You want to find the easiest way to do your math. Easiest correct way. Okay, easiest correct way. Got to be correct. Okay? Any more questions about this one? Because you'll have to do a few of these, and there'll be more complicated ones later, but this is the idea.
The lemma we learned in 2.2 was that for a delta greater than 0, you can use an epsilon. And
yep.
In this case, we're just changing notation.
Yeah, I mean, well, actually, so this, remember, and this is another thing you've got to get used to, and I've talked to students in office hours about this. When a theorem is stated, you got to pick some letters, right? Greek ones, Latin ones, whatever. You got to pick some letters to state it. When you're applying the theorem, you may not be using the same letters. So what you have to do is get used to not thinking about a theorem as being a thing about certain letters. You have to think about a theorem as being about certain objects, and the names may change, to protect the innocent. Okay, sorry. But anyway, couldn't resist. Right? And so you have to not think about them as specific letters. So in there, I mean, I don't even usually remember what, I might even, if I were to state it now, change delta and epsilon from what I stated originally, right? It doesn't make the statement wrong or even different, right? Except in a very formal sense. And so what that said is that if you have a positive, what the lemma said without any letters, okay? What the lemma said is that if you have a positive quantity, and I explained this is positive, right? So if you have a positive quantity, then you can choose another positive quantity that is less than it. No letters, okay? You got to use letters when you write it down, right? But the way you should have it in your mind is the letters don't matter. All right? Yes?
So the mins are the positive quantities and the delta is the positive quantity that's less than that?
Yeah, I think it was even called delta in the lemma, right? Okay? So, or the exercise or whatever it was. And again, it doesn't matter what it was. We proved it one way or another, okay? But, so, delta is playing the role of delta in the original statement, if I remember correctly, and this thing here is playing the role of epsilon. So all you have to do to check to make sure you can use that is this a positive quantity? And if it's a positive quantity, you can play the role of epsilon in that theorem. Okay, and why is it positive? Because a half is positive and epsilon is positive. One of them is the minimum, right? That was also something I did in class, right? If you have two things, one is the min, one is the max, and you don't know which one is which here because you don't know how big epsilon is. It could be bigger than a half, it could be less than a half. But it doesn't matter because one of them is the minimum and both of them are positive. So whichever one it is, this whole quantity is positive. See how we keep using stuff that we've done earlier, right? We keep using stuff, and that's why you got to know all that stuff.
I guess what this means, the limit says If delta greater than 0, can exist some epsilon such that epsilon is...
Okay, so I remembered them in reverse. Okay, so then if that's the way the statement says, so it gives you a delta and then you can find an epsilon. Is that the way it's stated exactly?
Well, you have an epsilon that is less than delta and greater than 0.
Right, okay, so what that means is, in fact, in the lemma, this is playing the role of delta and this is playing the role of epsilon. But again, you shouldn't think about the particular letters, because if you do that, you're going to get confused about it, right? You should think, there's this thing that happens to be called delta or epsilon in the lemma, and there's this other thing, right, which happens to be called something in the lemma, but you've got different names for things, and so you've got to identify what's playing the role of what. And you may think, well, that's really unpleasant. Why can't we just use the same ones all the time? Well, because you kind of run out of things, right? You kind of run out of things. And so you're going to have to reuse letters, and so you just need to get used to it. You'll see that several times in these homework exercises where you have to go back and use a previous theorem, and you have to look at what plays the role of what. Okay, let's move on, because I really need to get around to our main theorem for today. So of course now we're always in the real numbers. There exists some S, an element of R. Let's just make it positive at the beginning, S bigger than 0. In fact, I want it unique. A unique S bigger than 0 such that S squared equals A. Okay, so even though Greeks knew how to find the diagonal of a square, which to them might tell you that the square root of anything exists, right? Because you just take a square of side length A and they could construct that. They would have been willing to believe that the square root of 2 exists based on that alone. There's a little bit of a problem, and that is that there are other real numbers that you can't construct. Okay, in fact, you've probably heard that famous problem about trisecting an angle. Okay, the reason why it was so important to the Greeks is that, if you derive the sort of reality of things by whether you can construct them, then if you can't construct something, then there's a bit of a problem, right? And so there are, in fact, numbers that can't be constructed in this way, like cosine 20 degrees. In fact, that's because that's non-constructible, that proves actually that you can't actually trisect all angles. You can't trisect a 60-degree angle. Okay, so constructing things alone isn't enough to get all real numbers. It won't get you that one, for example. Okay, but this completeness axiom gets you everything. It gets you non-constructible things. It gets you that. It gets every possible real number that you need. Fills in all the holes. Now this proof is going to take some time. It's the most complicated proof we've done yet, but even this proof, like pretty much all proofs, breaks down into simpler proofs. So it's kind of composed of a lot of things, and you need to be able to do this proof. And the way you will learn to do this proof is by learning the outline and then being able to do the calculations that are connected with it. So for example, you may think that I memorize everything that I do before I come in here, but my memory is not good enough for that. Okay, so all I feel like I need to remember is what the basic steps are, and then trust that I can fill in the details as we go along. Okay, so now I'm going to start with something that you will only see the value of later, okay? And this is something that often happens in proofs, though. You start by reducing your proof to an easier situation that really isn't much worse, much easier, or sorry, the general situation really isn't much worse, that it follows rapidly from the special case that you do. So that's sort of identifying a good special case that has all the work in it, but is a little bit simpler. And you'll see that in play right now, okay? So the first thing I'm going to start with is I'm going to suppose A is bigger than 1. Now you'll see the value of this, it will come in over and over again, but really the reason I'm doing this, just to give you a heads up, is that when I'm bigger than 1, I know what happens when I square, right? What happens when you square something that's bigger than 1? It gets bigger. Okay? Whereas if you're, well, okay, but it gets bigger too, right? Whereas if you square something that's less than 1, what happens? It gets smaller. And so if we allow all these things to be happening at once, then we're not going to be able to keep control over our inequalities when we square things. And squaring is what this is all about, right? Okay, so we're going to start with that, and then we'll go back and do a equal 1. Well, that's easy. Okay, and then we'll do a less than 1 at the end sort of quickly. Okay. So here's what I'm going to do. I have to use the completeness axiom to do this, and so I need a nice set that I'm going to find the soup of, right? Because the soup of things is supposed to fill in all these holes, so the soup should let me find this guy. Okay, so I'm going to let A be the set of all x greater than 0, such that x squared is less than A.